Today we're going to talk about calculating limits using the limit laws. So let's start by discussing what these limit laws are. Suppose that c is a constant and that the limit as x approaches a of f of x and the limit as x approaches a of g of x both exist. Then the first one says that the limit as x approaches a of f of x plus g of x would be the limit as x approaches a of f of x plus the limit as x approaches a of g of x. The second one says if you're taking the limit of two functions being subtracted, you can take the limit of each of those functions and just subtract them. The third one says if you're taking the limit as x approaches a of a constant times a function, you can actually pull that constant out and multiply it to that limit at the end, and so carry it through. The fourth one says if you're taking the limit of two functions being multiplied, you can actually just take the limit of the first times the limit of the second. If you're taking the limit of two functions being divided, you can take the limit of the numerator and divide it by the limit of the denominator, provided, of course, that the denominator is not equal to 0. The next one says if you're taking the limit of a function that's being raised to a power, you can actually just take the limit of that function and then raise it to that power where n is a positive integer. The limit as x approaches a of any constant is just that constant. If there's no x in there, if there's no variable, then the limit is just itself. The limit as x approaches a of x is a, so it's that one kind of gives you permission to essentially plug in x equals a. The limit as x approaches a of x to the n would be a to the n, kind of like that last one. This one essentially, again, gives you permission to plug in x equals a, but for this one, n needs to be a positive integer. The limit as x approaches a of the nth root of x is the nth root of a, where n is a positive integer. And of course, as n is even, then a would need to be a positive value, because you can't take the even root of a negative number. And the limit as x approaches a of the nth root of a function, you can actually pull that radical out, take the limit of that function, and then take the nth root. And of course, n would have to be a positive as well, integer as well. So let's look at an example. What if we wanted to take the limit as x approaches 2 of x squared plus 4x minus 11? At this point, the way we've been doing it is we've been making those tables where we plug in values like 1.9, 1.99, 1.999, 2.1, 2.01, 2.001. Let's apply these limit laws instead. So if we apply limit law 1 and 2, we can break this up into the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 4x minus the limit as x approaches 2 of 11. Then, using limit law number 3, we can pull this coefficient out. So it's 4 times the limit as x approaches 2 of x. Now, using the limit laws 9, 8, and 7, the limit as x approaches 2 of x squared is 2 squared. The limit 4 times the limit as x approaches 2 of x would be 4 times 2. And then the limit as x approaches 2 of 11 would just be 11. Put that all together, and we would get that the limit as x approaches 2 of x squared plus 4x minus 11 is just 1. Let's do another one. The limit as x approaches negative 3 of 4x minus 3 over x minus 2. Using limit law number 5, we can take the limit as x approaches negative 3 of the numerator over the limit as x approaches negative 3 of the denominator. Using limit law 2, taking the limit of two things being subtracted, you can take the limit of the first minus the limit of the second. Using limit law number 3, we can pull this coefficient out front, kind of like we did in that last example. And then using limit laws 8 and 9, the limit as x approaches negative 3 of x is just negative 3, and the limit as x approaches negative 3 of a number is just that number itself. And we see that the limit as x approaches negative 3 of 4x minus 3 over x minus 2 is just 3. Now, with those two examples, what did we notice? We noticed that the limit as x approaches a of f of x actually just turned out to be f evaluated at a. And so when you're evaluating limits, you want to try something called direct substitution, where you directly substitute in x equals a. If f of a is a real defined value, then the limit as x approaches a of f of x is that value, f of a. However, this is very important, if f of a is not a real defined value, that does not mean that the limit doesn't exist. All that means is that direct substitution did not work, and you will need to try another method. And there's lots of different methods we're going to discuss. All right, so let's do some examples finding the limit. The limit as t approaches -2 of 3t cubed plus 5t squared minus 6t plus 7. Let's try direct substitution, where we directly substitute in t equals -2. And when we do that, 3 times -2 cubed plus 5 times -2 squared minus 6 times -2 plus 7, we get 15. 15 is a real defined value, so that limit does exist and it's equal to 15. Let's try another one. The limit as w approaches 3 of w squared minus 9 over w plus 3. Again, we'll try direct substitution. If we get a real defined value, we're done. So when we plug in w equals 3, we get 3 squared minus 9 over 3 plus 3, which gives us 0 over 6, which is 0. 0 is a real defined value, so that limit does exist. It's just equal to 0. Let's try another one. The limit as x approaches 2 of x squared minus 4 over x minus 2. Now, what happens when we do direct substitution? We plug in x equals 2, we get 2 squared minus 4 over 2 minus 2, which gives us 0 over 0. That is an indeterminate form. We refer to that as being undefined. That doesn't mean that the limit doesn't exist. That just means that direct substitution didn't work, and we're going to need to try another method. So I have a fact for you. If f of x is equal to g of x for all values except at a, but they're equal for any other value but a, then the limit as x approaches a of f of x would equal the limit as x approaches a of g of x. Of course, provided that the limit does exist. So let's look at that x squared minus 4 over x minus 2. We can actually factor the numerator into x plus 2 over times x minus 2. Now notice you have x minus 2 over x minus 2. Those will cancel, and we get x plus 2. So it turns out that x squared minus 4 over x minus 2 is equal to x plus 2 for all values except for x equals 2, because again, here you can't plug in x equals 2. So using the fact that we just discussed, the limit as x approaches 2 of x squared minus 4 over x minus 2 is equal to the limit as x approaches 2 of x plus 2. Now we can try that direct substitution to get 2 plus 2, which gives us 4. So let's try a few examples. If we were going to take the limit as x approaches -1 of this function here, we could try direct substitution, but when I plug in -1, I end up with 0 over 0, which again, that's an indeterminate thing, which we would refer to as undefined, because dividing by 0 is undefined. So direct substitution doesn't work. Again, that does not mean that the limit doesn't exist. That just means that direct substitution doesn't work and you need to try another method. So let's see if we can find another function that is equal to this function here for all values except at -1. So we'll try factoring. So if we factor the numerator completely and factor the denominator completely, notice they have a common factor of x plus 1. When you get rid of that x plus 1, we have the limit as x approaches -1 of 2x plus 1 over x minus 6. Now let's try our direct substitution. When we plug in x equals -1, we get 1/7, which is a real defined value, which means that this limit actually does exist and it's equal to 1 over 7. Let's try some more examples. Let's look at the limit as h approaches 0. Now, of this function here. Now we can see right here, we can't plug in h equals 0 because that's going to cause us to divide by 0 right away. Well, it's really hard to factor the numerator because it's not a bunch of terms being added and subtracted. So in order to even consider the idea of factoring, we're going to need to distribute this out first. So 3 plus h squared is 3h times 3h. So everybody in the first group will get multiplied to everybody in the second group. And we get 9 plus 6h plus h squared minus 9. Now notice the positive 9 and the negative 9 are going to cancel. And now we have 6h plus h squared. Both of those have an h, so let's factor one out. And when you factor that h out, notice this h and this h are going to cancel. And so we're left with the limit as h approaches 0 of 6 plus h. So this function here and this function here are the same for all values except h equals 0, which means their limits will be the same. So when I take the limit as h approaches 0, I'll try my direct substitution by plugging in h equals 0, and I get 6, which is a real defined value, so this limit does exist, and it's equal to 6. Now, what about the limit as t approaches 0 of this function here? As you can see, factoring isn't going to be an option here. And it's not like the last one where we can just square the term and distribute, or what you would refer to as FOIL. We actually have to take the square root here, which is not something we can distribute. So the trick we're going to do here is something that you probably learned in maybe your Algebra 2 class called multiply by the conjugate. And this works when you have a square root minus a value or the square root plus a value. The conjugate is the exact same thing except the opposite sign. So this minus becomes a positive. Now you can do whatever you want to a fraction as long as whatever you do to the numerator you do to the denominator. Because notice, something over itself is 1, and you can multiply by 1 all day long and not change it. So now to multiply these two fractions, I'll multiply their numerators together and their denominators together. Now when I distribute, or what you would call FOIL, I would do the first, outside, inside, last here. And then that square root of t squared plus 9 times the square root of t squared plus 9 is the square root of t squared plus 9 squared. Then I would have this times the positive 3, the negative 3 times that, and negative 3 times positive 3 is negative 9. Now notice this is positive 3 of that square root of t squared plus 9, and minus 3 of that square root of t squared plus 9. Those two terms are going to cancel. When I square this square root, those cancel, and I have t squared plus 9. This cancels with this, and I have a minus 9. Now what you notice is this positive 9 and minus 9 are going to cancel. And when they do, I'm left with t squared over t squared. Hey, look at that. Those are going to cancel. And now that I have it in this form, let's now try to plug in t equals 0. Right here, this t equals 0, 0 squared times anything is 0, was giving us 0 in the denominator, which was preventing us from being able to take this limit by direct substitution. Let's now try to directly substitute in that t equals 0, and we get 1 over 3 plus 3, or 1 over 6. So that is a real defined value. This limit does in fact exist. And if you look back in your notes from the previous section, this actual limit should look familiar to you as we did it using the table method. Okay, so we're going to pause here and we'll have a part 2 video where we do some more methods of taking limits, and I'll see you in the next video.